What are parametric equations? In the abstract, parametric equations in 2 dimensions are systems of equations. X and Y are both dependent variables. Both. This is different than usual. Dependent variables of some parameter, usually called t. And we call it t because it usually represents time. This is a system of parametric equations. The most common application of parametric equations is to modeling motion in physics. Most common example is free fall. We've talked about up-down motion in free fall, but now with parametric equations, we can allow ourselves to model motion actually along a parabola, like you're throwing a ball sideways and not just up straight in the air. We can talk about that kind of thing. Before we do that, though, it's good to think about simpler cases, like modeling motion along a straight line at a constant speed, including not just left to right motion as you typically draw graphs, but also right to left motion. Maybe we start at this point. Let's say the coordinates of this point are 3, 4. And we head off in this direction. As time goes by, imagine maybe it's like a bug starting there. Remember trig bug? Okay, now it's not trig bug, it's straight line bug. Straight line bug starting right here when t equals 0 at time 0 and is traveling left to right at a constant speed. And this bug, let's say, ends at the point -9, -1, when t equals, let's just say 4, just to make something up. So it's like 4 seconds of time, the bug has traveled from this point to this point at a constant speed. We can use parametric equations to model the x and y coordinates of that bug at the same time. You think of these equations as a pair. They go together. That's very conceptually important. It's important to label your axes, in this case, x and y. To help us figure out parametric equations to model this motion, though, we want to think about 2 other sets of axes. One labeled t and x, and another one labeled t and y. I'm trying to find 2 functions of t that together model this motion. How would you find them? Use the given conditions. Focus first on x. X goes from 3 down to -9 as t goes from 0 to 4. 3 down to -9 as t goes from 0 to 4. And if the bug is traveling at a constant speed, I hope it makes sense that you'd want to use a straight line here. That's supposed to be a straight line, even though it doesn't quite look straight. So that should be a graph giving us the x coordinate of the bug's location as a function of time. X equals f of t. And hey, I could figure out a formula for that. It's a straight line, right? Find the slope and the intercept. The intercept's easy. That's 3, vertical intercept. What about the slope? Rise over run. Well, the rise is negative. Delta x is -9 minus 3 is -12, indicating x has decreased. And the run is, well, 4. This is really an average speed in the average velocity in the x direction. -12 over 4, -3. This is delta t. delta x over delta t is going to be negative 12 over 4, which is negative 3. That is the slope of that line, and it's also the what you might call the x component of the velocity. And this equation is negative 3t plus 3. Y, on the other hand, starts at 4 and goes down to negative 1 as t goes from 0 to 4. And once again, since the speed of the bug is constant, this should also be a straight line. Delta y is negative 5. Delta t is still 4. The velocity in the y direction is negative 5 over 4, which is negative 5 force. If time was measured in seconds and distance was measured in centimeters, as it would be for bugs, say, this negative 3 would be negative 3 centimeters per second. This negative 5 force would be negative 5 force centimeters per second. You do want to keep the negative signs there. We're talking about velocity, not speed, to keep track of how fast x and y are changing, in this case, negatively. They are decreasing. So y is a function of time. Y equals g of t is negative 5 force t plus 4. These two equations together form the system of parametric equations that describes the motion of the bug as t varies between 0 and 4. That would be your description of the motion. This is called kinematics in physics, describing motion with equations, not dynamics. We're not trying to understand the motion using physical laws. No F equals ma here. We're just trying to describe the motion mathematically with parametric equations in this case. It's worth probably double checking that f of 0 comma g of 0 is the starting point. Plug in t equals 0, you get the 0.34. Yep, that's right. That is the same as the starting point up here. And when you plug in t equals 4, f of 4 comma g of 4, do you get the ending point? Plug in t equals 4 there. Negative 3 times 4 is negative 12. Negative 12 plus 3 is negative 9. Plug in 4 here. Negative 5 force times 4. The force cancel is negative 5 plus 4 is negative 1. Negative 9, negative 1. That's the coordinates of the ending point right there. You could also double check points in between. Okay? You need to use your imagination. You need to imagine a bug literally moving on this line as time goes by. With a calculator, it's fairly easy to do the imagination. The calculator does the imagining for you. Go to your mode button, your mode screen, change from function to par. Stands for parametric. Functions, ordinary functions. Par means parametric. Pole means polar. Sequence means sequence. We want par for parametric. When you go to your y equals screen now, it will look different than usual. You want to plug in both of these functions. X is negative 3t. Hey, I made a t instead of an x. Plus 3. I pressed the same button. It's still the button with the x there, but it made it into a t. And y equals negative 1.25 t plus 4. Negative 5 force is negative 1.25. When you go to your window, you want not only scales in the x and y directions, but also a scale for t. T is going to go from 0 to 4. T step of, say, 0.1. My x min and max and y min and max are negative 10 and 10. That seems reasonable to keep those as they are. I'm about to hit graph. When I hit graph, watch that the graph is traced out not from left to right like usual, but from right to left. We are seeing the motion. Ready? 1, 2, 3, go. There it is. If I make my t steps smaller, like 0.01 instead of 0.1, and graph it, I'll see the same curve, but it will be traced out slower, a little easier to see. You can even try to time it to be real time, 4 seconds. I didn't do that. I don't know if it was 4 seconds or not. Seemed close. To try to see what the bug's actually doing in real time, you might say. You should be able to eliminate the parameter. In simple situations, at least. In harder situations, it can be very hard or impossible to eliminate the parameter, but this is simple enough that we can. What does it mean to eliminate the parameter? It means get rid of it. How? Well, in this case, we could say take the second equation. Well, maybe it's better to take the first equation. Let's take the first equation. Solve for t in terms of x. Get t as a function of x. Effectively find the inverse function of this, which can be done here. And then take that and plug it into this equation in place of t. If you do that, I hope in your mind you realize the t's are going to go away. You get an equation only involving x and y. First, subtract t from both sides. Or subtract 3, yep, from both sides. Then divide both sides by -3. Maybe you prefer writing this as 1 minus x over 3. That's okay. Either way is okay. Now substitute that into the y equation in place of t. Get y equals -5/4. T gets replaced by 1 minus x over 3. Don't forget the +4. I'm looking at this equation right here. I'm replacing t with 1 minus x over 3. Simplify. The t's have gone away, but simplify. Distribute the -5/4 through the parentheses. This becomes -5/4 plus, let's see, 5/12 x, right? -5/4 times -1/3 will be +5/12 plus 4, which is 16/4. This simplifies to y equals 5/12 x. 16/4 minus 5/4 is 11/4. 11/4 is the same as 2.75 if you prefer. 5/12 could be converted to a decimal as well, but I think it's a repeating decimal. 5/12, yeah, 0.416 repeating. What have we done? What's the value in eliminating the parameter? Just for fun? Well, I hope you think it is fun, but that's not the only reason. It's telling you what line the bug is traveling on in the XY plane, irrespective of what's going on with time t. It's traveling on a line with a slope of 5/12 and a y-intercept of 11/4. This red line up here has a slope of 5/12 and a y-intercept of 11/4. Not saying what time t it is when the bug crosses the y-axis. We could try to figure that out. It's something you should be able to do. Let's go ahead and do that. When does the bug cross the y-axis? I could ask, when is xy equal to 0.11/4? I could take either one of those numbers, 0 or 11/4, set this one either equal to 0 or this one equal to 11/4 and solve for t, and I should get the same answer either way. You only have to do one of them, but let's do both of them to see that we get the same answer. If I set x equal to 0 and solve for t, there's what x equals. I will get a nice number, t equals 1. I hope that happens with the other one. Let's see if it does. If I set y equal to 11/4, the y equation is -5/4 t plus 4, setting this equal to 11/4, and subtracting 4 from both sides. 4 is 16/4, 11/4 minus 16/4. Hey, yeah, it's -5/4. T is 1. So the bug is crossing the y-axis when t is 1. I didn't have to do both of these lines. I wanted to do both of them to see that I got the same thing. Math is consistent if you do it right. Don't make mistakes. So that's another thing you should be able to do. I also want you to notice that the slope of this line, 5/12, that's the slope of that line, is the same as what? It's the same as the ratio of the derivative of this function to the derivative of this function. If I compute dy dt and divide it by dx dt, for this example, what do I get? I get the ratio of two constants, -5/4 and -3. The negative signs cancel, and this simplifies to 5/12, the slope of the line. That's not an accident. You could call this dy dx if you liked. It's almost as if in this fraction you can cancel the dt's. Oh, can we really cancel the dt's? Not really, but remember, I've said this before, in calculus, calculus is full of convenient fictions. Things that you can pretend are true, and they give you right answers, but they're not literally true. Unless you use infinitesimal numbers, which we're not doing, and is a graduate school level kind of thing, so we don't do it. Yeah, it's as if you can cancel the dt's, and dy dt over dx dt becomes dy dx, and it does give you the right answer for the slope here. Not so surprising because it's a straight line, but this relationship actually holds even for curves. It's amazing. Even when the path of motion is not a straight line. It's also important to not only be able to figure out velocities in, say, the x and y direction, like we did. The velocity in the x direction was -3. The velocity in the y direction was -5/4, but figure out the overall velocity and the speed, and those are different things. What I'm about to tell you is very important for multivariable calculus. We can combine these parametric equations into what's called a vector. Scary word. Some of you are familiar with vectors, some of you maybe not. In particular, a position vector is what we could start off with. Position vector. In physics, in this kind of situation, you'll typically see this written as f of t I hat. Yes, that's an I with a little hat above it. That pointy thing is a hat. The I is wearing a hat. Where's the dot for the I? Well, we don't bother making it. Plus g of t j hat, and we don't bother making the dot for the j either. The j is also wearing a little hat. What in the world is this? It's notation to represent the position of the bug as it moves in terms of what's called a position vector. Well, what does that mean? So here's the bug. The bug starts here and is heading off this direction. At a certain moment in time, okay, so it started here when t was 0, and it's here when t is, say, 0.5. At that moment in time, t equals 0.5, the bug has a certain position in the plane, which can be represented just with the picture, but it can also be represented with an arrow starting at the origin and going to that point. That arrow is the position vector. In physics, vectors are arrows. That's how we draw them, at least. They are directed quantities. Quantities with a magnitude. In this case, the magnitude is the distance to the origin, and a direction. The direction is effectively, where are you compared to the origin? The direction of this arrow goes from the origin to the location of the bug at that moment in time. What is the I hat and the j hat? Those are called standard unit vectors. I hat points directly to the right. J hat points directly upward. And they have unit length. If you're measuring distance in centimeters, they would be 1 centimeter long. We're representing this position vector. Let's pretend this is I hat here in this picture, and this is j hat. I'm making them smaller. We're representing this green position vector, the bigger one, as a sum of scalar multiples of I hat and j hat. If f of t is, for example, 2, just to pick a number, 2 I hat is an arrow pointing in the same direction as I hat, but twice as long. Say about like that. Starting at the origin still, that would be 2 I hat. And if g of t is, say, just to pick a number, 4, then this arrow going from the origin parallel to j hat, but 4 times longer, that would be 4 j hat. Now, I just picked numbers out of the air. I don't know that it's consistent with this line. It probably is not. Yeah, it definitely is not. Maybe I shouldn't have used 2 and 4. Let's call this f of t I hat and g of t j hat. And the position vector itself is a sum of those, in the sense that if you make a rectangle like this, the position vector goes from the lower left corner at the origin to the upper right corner at the location of the bug when t equals 0.5. Based on this position vector, I can find something called the velocity vector. By differentiating f and g and putting those things in front of the I hat and j hat. F prime of t times I hat plus g prime of t times j hat. What is f prime for our example? It's -3. What is g prime? It's -5/4 for our example. By the way, I also could have simplified this one for our example. I could have replaced f of t with -3t plus 3 and g of t with -5/4 t plus 4. I could have done that before, and I'm doing it now. This vector, the position vector, is not constant because the bug is moving. The velocity vector for our example is constant. This vector always points in the same direction and always has the same length. If you started its arrow at the origin, it would look about like this. This part would represent -3 I hat. This part, this component they're called, would represent -5/4 j hat. The negative signs keep track of the fact that this arrow points the opposite direction as I hat, and this arrow points the opposite direction as j hat. And I'm effectively adding them together, making a rectangle like this. And the resultant vector, this velocity vector, starts at the origin again and ends at the opposite side of that rectangle. When you interpret the velocity vector for this example, however, you don't put it at the origin. you put it at whatever location the bug is at whatever moment in time you're talking about. And it will be, because of this, the motion is along the straight line, it will be parallel to this line with the slope of 5/12. No matter what t is, the slope of this arrow effectively is 5/12. The ratio of -5/4 to -3. Just like we saw before. But as the bug moves, you actually imagine the velocity vector moving with it. Based on the velocity vector, we can also compute something called the speed. And yes, speed and velocity are different. For up-down motion, as we've talked about before this point, if the vertical upward direction is considered to be positive, upward motion is positive velocity, downward motion is negative velocity. But now this is not up-down motion. This is moving through a plane motion, including left-right motion. We need to keep track of that. The velocity vector does so. The speed is the magnitude of the velocity vector. Magnitude of velocity vector. Whereas the velocity vector is a number, the speed is not a, the velocity vector is a vector, the speed is a number, not a vector. It can be found with the Pythagorean theorem. Take the components. This does form a right triangle here and here. I can use the Pythagorean theorem to figure out the magnitude or length of that velocity vector like this. Simplify. I think this simplifies nicely to 144 plus 25 over 16. 169 over 16, and that has a nice square root. It's 13/4. 3.25 in units would be centimeters per second. How about that? It came out nice. I purposely made the example to come out fairly nice. Is that the only way the speed could be computed here? No. A more direct way to find the speed would be use the Pythagorean theorem here. Figure out the distance traveled and divide by the time elapsed, 4. The Pythagorean theorem means the length of the hypotenuse here is the square root of 12 squared plus 5 squared. Square root of 169 is 13. And it travels over 4 seconds, 13/4. That's definitely a quicker way to find the speed in this case. But, this is a big but, it only applies for constant speed motion. Otherwise, it's just an average speed, not an instantaneous speed. Whereas this formula gives you an instantaneous speed and in general is a function of t. This becomes more significant when we talk about non-constant speed motion, though the simplest non-constant speed motion, I'm still going to do a constant speed motion, but it's not along a straight line. The simplest non-constant velocity motion is circular motion at a constant speed. And the simplest example of that is x equals cos t, y equals sine t. As t varies between, what should we pick? How about 0 to 2 pi? Oh, this is the bug. Trig bug. When t is 0, cosine of 0 is 1, sine of 0 is 0. Trig bug is at the point 1, 0. When t equals 0. And as t increases, by definition of cosine and sine, according to trig bug, we need to stay on the unit circle, traveling around counterclockwise at a constant speed. This is still constant speed. Until we get back where we started, also when t equals 2 pi. Counterclockwise motion. The position vector is not constant because the bug is moving. It's f of t I hat plus g of t j hat cosine of t I hat plus sine of t j hat. What's the velocity vector? Differentiate each component. These things in front of the I hat and j hat are called components, or some people say components, but I say components. F prime is negative sine t. G prime is cos t. Where is the velocity vector? It's nowhere and everywhere. You want to draw it at any moment in time to start on the curve. So if we're at a moment in time, say, for example, t equals, I'm going to pick 1.5, a little less than pi over 2 on purpose. The position vector is going to look like that. That'll be the position vector. And the velocity vector, you don't want to start at the origin. You want to start it at the location of the bug. It turns out to point this direction. That'll be the velocity vector. You can plug in t equals 1.5 to see what these numbers are. As the bug continues to move, those vectors do change, not in magnitude, but in direction. The position vector rotates around, keeping track of the fact that the bug is going around the circle. And the velocity vector rotates around as well and always stays tangent to the curve, because it's always pointing in the instantaneous direction of motion at any moment in time. The speed is constant. It's the square root in general of f prime of t squared plus g prime of t squared. In general, that's not a constant function, but in this case it is, because we can use a trigonometric identity to simplify this. We get sine squared plus cos squared. It simplifies to square root of 1 centimeter per second, say. Does that make sense? The bug is traveling around the unit circle, 1 rotation counterclockwise in 2 pi units of time. But what's the circumference of the unit circle? 2 pi. Distance traveled 2 pi divided by time elapsed 2 pi is 1. We could figure out this constant speed another way. But to end class today, let's do a fun non-constant speed example. We won't have time to do everything in this section in class today. There are some problem-solving problems related to other things. Sorry that there always is the case. It's never really enough time to do everything in the book in class. We'll do more on Wednesday before we review for the exam. What if I let f of t be a cosine with, say, a 3 in front of the t, and g of t be a sine with, say, a 5 in front of the t? It's a cosine and a sine with different frequencies. As t varies, will this trace out the unit circle? The answer is no, because the frequencies are different. What will it trace out? Something beautiful. In order to see the actual motion with Mathematica, parametric plot, which plots parametric curves, is not good enough because it gives you the ending curve. We want to see the actual motion. So unfortunately, in Mathematica, it's not quite as nice as a calculator. You have to do a little funny thing here. You have to make the right endpoint of the t interval some parameter that you can vary. Inside, manipulate. Start b just barely bigger than 0 and go up to 2 pi. This parametric plot now this code effectively is inside the manipulate code. Manipulate will make animations, and that's what we want. We want to see the bug moving. B goes from 0 to 2 pi. If I don't add any more formatting commands, it's not quite ideal. I want to add another formatting command, effectively plot range arrow. I'm going to put a 1.2 there. What will we see when we enter this? We will not see a circle. Instead, we see a beautiful curve called a Lissajous curve. That is the bug's motion in this case, and there we go. It's very pretty. Pretty interesting. The speed is not constant. If you find the speed in this case, take the square root of f prime of t squared plus g prime of t squared. You do not get a constant function. It slows down in the tight turns. I want to go slower. That's what I need to press. It slows down in the tighter turns and speeds up in the straightaways. It literally does. Okay. Much more interesting and also more related to what we're going to do in chapter 5 on integration. We're going to be using this kind of example a lot. Okay. Again, I didn't have time for everything in this section. In particular, I'm thinking of I hinted at the general formula for dy dx. I'll just say it to you verbally here. It was dy dt divided by dt dx. You can use parametric equations still to find slopes. You should be able to do that.